have another absolute value equation for you. Now, lately I've been insisting on using this definition of absolute value that says the absolute value of A is the square root of A squared. I kind of like it, you don't have to break it down into two cases. And so it has its value, but I mean, it can be kind of messy. And this problem that I'm working tonight ended up being relatively messy. And I'm still not even sure how to really work this problem, breaking it down into two cases based on this definition of the absolute value. So I will be using the square root of A squared definition. Okay, so y'all, here's our equation. Now, at first you think, oh, there could be no answer because how can the absolute value be negative? But this says the absolute value of something minus the absolute value of something. And that can be negative if this expression on the right-hand side has a larger magnitude. Okay, so here we go. And this very first line is just, it's normally a good thing to isolate one of the absolute value bars on one side. And also, if you think that is the square root definition, that's the same thing when you're doing radical equations. You're better off isolating one of the radicals. It just makes your life a little bit easier. Otherwise, you're having to do a binomial that contains two radicals, and it may be hard to eliminate the radical. So it's the same kind of reasoning here. Now, so all I did on this very first step was just bring the absolute value of x plus 2 to the other side. And then at this stage right here, I just changed it to the absolute value definition. See, here this says absolute value of x minus 7 over 3. Well, the square root of the quantity x minus 7 over 3 squared is the absolute value of it based on this definition here, and the same right here. Now, notice here that this right-hand side is in the form a minus b quantity squared. And you know how it goes when you're doing radical equations. You have to square both sides. That's what we're doing here. When you square this side, that radical just goes away and you're left with this piece right here. Okay. Now, the result of this, I tried to show you here. This is just the expansion of a squared minus 2ab plus b squared. Okay. So it looks like we've made some progress here because all we have left is just a single radical, which is good news. Now, what I did right here is I just got everything together on one side, and I got this, I got the only square root or radical piece isolated by itself. Now, so here's really what happened. Now, I didn't show all of this messy work right here. You end up having to subtract this expansion from this expansion. So, I mean, I did it, and then I did verify it with a symbolic algebra checker thing. I didn't want to go to the trouble to show you guys something that had any typos in it. But anyway, notice a good thing happens here. See, you have an x squared term here and an x squared term here. So you can see in advance, the result of this is just going to be some kind of linear expression, right? This is going to be x squared. This is going to be x squared. And so the x squareds will cancel, and you'll get something that's a little more tractable than if that weren't the case. So let's go to the next line. Now, this looks like a mess, but at least you're not stuck with an x squared term. Okay? And so I rewrote it. It seems simpler to just multiply by 9 and get this equivalent equation right here. Now, again, though, we're going to have to square this. And this got very messy. And I'll tell you, I let the computer expand this out just to make sure I didn't make any mistakes. You know, it's something we can all do, but it's just a very tedious process. So this line right here is the result of raising this binomial to the second power. Okay, I raised this binomial to the second power and got this nasty looking expression. And I about quit here. These numbers look way too big. Now, also, when you square this out, you get another very messy looking thing here. All right. So all that looks messy, but you remember they're equal to each other. And so notice what happens when you subtract this term from this like term right over here, right? It works out pretty nicely. It knocks it all the way down to 900. If you deduct this number 5184 from 6084, you're left with 900, right? So that's something, at least it's a 3-digit number, all right? Now, the same thing with the linear terms. If you subtract this guy right here from this term right here, you just end up with minus 300x. You're going, maybe there's some hope. Now, it looks bad here, though, because when you subtract this constant term from this constant term, you get minus 3575. But you know what? We caught a break here, guys, because all three of these numbers, 900, 300, and 3575, are divisible by 25. I mean, we got lucky there. So we divide this entire equation by 25, and this is what happens. I just rewrote it here. And so we get a quadratic that looks quite manageable. Now we, again, more breaks, we caught a break here because 143 only has it's almost prime. It's 11 times 13, right? 143 is 11 times 13. And so now right here, I did spend, you're not seeing the time I spent. I tried it with 3 and 12, thinking that might work. It didn't look like 36x and 1x would work. So I tried 3 and 12, did some trial and error, it didn't work. I knew we're going to have some nice answers because I did look at the discriminant here and it came out to be a perfect square. But so it turned out 6x and 6x did the trick. And you can verify that when you expand these two binomials, you actually get this piece right here. But again, this constant term being the product of two prime factors was useful. And so it turned out that the blue one, the 13 over 6, is the only one that worked. When you work these kind of problems in your squaring, you can introduce extraneous solutions. It turns out minus 11 over 6 is extraneous. But let's take a look at this 13 over 6. Let's take it back to the original 13 over 6. All right. Now, so here's what we set out to solve, folks. Now, if you put 13 over 6 right here, 7 over 3 becomes 14 over 6. So 13 over 6 minus 14 over 6 is minus 1 over 6. Take the absolute value, that's 1 over 6. Now, if you put 13, so remember we have 1 over 6 is the result here. Now, if you put 13 over 6 here, this ends up being 25 over 6. 13 over 6 minus or plus 12 over 6 would be 25 over 6. But 1 over 6 minus 25 over 6 is minus 24 over 6, which is minus 4. So that works. That works just fine. Now, you guys can, if you don't, you can check minus 11.6. It doesn't work. It's just the negative opposite. It's close, but it didn't count because it came out to be 4, I think. So, y'all, these are our two solutions. And I thought it was interesting that the solutions were contained in the zeros of this quadratic equation. This all was nasty here, a lot of hard work that could have, most of it was done by hand, but I did use the computer to check when I had to expand out, like expanding this binomial is nasty, to do it by hand. So, but anyway, just one last thing. I'm still not sure I know how to work a problem like this in this case-by-case method. So any of y'all want to leave a comment, do that, all right? It's just, I know if there's just one absolute value expression, I have no trouble. But if there's two absolute value expressions and you're subtracting them and then that equals a negative number, or even when you write it in the equivalent fashion with this on the other side, it's still difficult. So y'all let me know what you think about that. And let me go ahead and that is the answer. And I wouldn't mind seeing a case by case in the comment if any of y'all want to do it. Thanks.